what happens to H2O as you start in the solid phase, ice, at minus 18 degrees, and what happens to it as you increase, you're always adding energy to it, okay? So we're doing an endothermic reaction because we're adding energy to the system. The system is the H2O, and it's starting in the solid phase. It's going to rise in temperature a little bit, and then when it hits the freezing point, something magical happens, and the temperature doesn't change as it's transitioning from the solid phase to the liquid phase. So if I zoom in on this red part of the curve, okay, when we first hit this mark right here, this is 100% solid. And as long as it's 100% solid, as we're adding energy to that solid, we're increasing its temperature. And as we started to learn, that's completely dependent on the specific heat capacity of H2O in the solid phase. But once it hits the melting point, something else happens, because that's that temperature under these conditions where now it can transition between the solid and the liquid phase. And there's going to be an equilibrium there somewhere between the left-hand side where it's 100% solid and on the right-hand side where it's 100% in the liquid phase. Oh, that looks really sloppy. 100% in the liquid phase. As long as it's somewhere in between there, if there's some solid, let's say it's 10% solid and 90% liquid, as we're continuing to add energy, that energy is still going to go into the phase change from the solid to the liquid. It's not until it's 100% in the liquid phase that the temperature will now start to rise as we are continuously adding energy as we're traversing along the x-axis here, okay? Now, in our discussion of why it is that the temperature isn't increasing, we had a lot of really good ideas out there, all right? And they were all valid. So I went back and watched. I didn't want to mislead you that some people suggested that there's bonding between the molecules, like hydrogen bonding was suggested, or other intermolecular, so attractive forces between the molecules. But that needs to be overcome as well. But there's also the internal forces, the potential energy of those bonds. And there's vibrational energy and rotational energy, all of that, right? You can just think of this in general as energy that goes into the phase change. That's where the energy is going. It's not going to increase the temperature. Okay, so the temperature doesn't change when we go from the solid to the liquid. That just, you can just think of that as it goes into the energy goes into the phase change. But once we're all in the same phase, the liquid phase, now as we continue to add energy, the temperature increases until we get to 100 degrees Celsius. That's the boiling point. And as I already have written for you, at the left-hand end of that, right, we're all 100% liquid here. But now we're at that temperature where we can undergo another phase change. So the same thing is happening here. The temperature doesn't change until we get to 100% in the gas phase. And then again, as we continue to add energy, now the temperature is going to increase. Now, we already talked about coffee cup calorimetry, and we understand the heat required, Q, required to get a certain mass to rise by a certain degree Celsius based on its specific heat capacity, the CP. Remember that from a couple lectures ago. So this CP, remember, that's the specific heat capacity. And in this case, we're talking about the specific heat capacity of H2O, but we're going to have different specific heat capacities for H2O depending on what state it's in. You've been using the specific heat capacity of H2O in the liquid phase in lab. That's the 4.184 joules per gram degree Celsius. And as you'll see, there's a different value, a different C sub P when we're in the solid phase and when we're in the gas phase, which means that for the same mass of H2O, we're going to experience a different change in temperature for the same amount of energy that we're adding to it, because this is going to be different. And you'll see that now because I'm going to take you through the math. Okay. So that's going to be true if we're in the solid phase, the liquid phase, or the gas phase. We're going to have different specific heat capacities. And then something else is going to be happening when we're undergoing a phase change. When we undergo phase change, we're going to be talking about two other metrics for the amount of energy necessary. That has to do with what I told you about up here, all these different delta H's. Delta H of combustion, delta H of solution. We did a couple of discussions on this one. Okay, but then I have circled here delta H of vaporization and delta H of fusion. Right, we're going to be working with those today. The delta H of fusion, that's the energy necessary to convert 1 mole of the material from the liquid phase to the solid phase, or from the solid phase to the liquid phase. Either way, that phase change requires a certain amount of energy per mole that's undergoing that phase change. The same is true if the phase changes between the liquid and the gaseous state. That's the delta H of vaporization. So we're going to be looking at that as well. Up here, this is going to be dictated by the delta H of vaporization. That's going to determine how much energy is absorbed by this system, this amount of H2O, as it's moving from the liquid to the gas state. Down in here, this is going to be dictated by the delta H of fusion. Now, I've written all over this slide, okay, so it looks like a mess. So let's now go through these individual steps and we're going to put some numbers to them, okay? Before we get there, let's talk a little bit more detail about delta H of fusion and delta H of vaporization. And remember, these are both subsets of what we would consider to be the delta H of the reaction. The reaction could be anything, okay? This is just the change in enthalpy of the reaction. And now we're going to talk about two specific reactions: the phase transition between solid and liquid, and the phase transition between liquid and gas. And this is what they're called. So you should get familiar with these names, okay? So let's talk about the delta H of fusion first. So that's going to be H2O moving from the solid phase to the liquid phase. As I mentioned, all of this is endothermic, right? We're continuously adding energy to the system, and that's what's getting the temperature to rise. And that's also what's getting, I think we all have practical experience with this. If you have ice and you want to turn it into water, you add energy to it, right? If you have water and you want to turn it into steam, you add energy to it. So those transitions are all endothermic. The system is absorbing the energy from the surroundings, okay? So this is an endothermic reaction. What's the sign, positive or negative, on enthalpy for an endothermic reaction? It's positive. Very good. So endothermic, so delta H is going to be a positive number because we're adding energy to the system. And we can actually look up what this value is. Here's a table from your textbook for different substances. Here's water down here, okay? And what we want on this table, right now we're working with delta H of fusion. Notice the units, delta H. The units are always in kilojoules per mole. And we look on here for water, the delta H of fusion is 6.01 kilojoules per mole. So what does that mean? Let's put that up here, all right? The delta H of fusion is equal to 6.01 kilojoules per mole. That means that when we undergo this reaction that I just wrote here, going from solid to liquid, okay, it takes 6.01 kilojoules of energy to melt 1 mole of H2O. And let me be specific. This is a positive 6.01 kilojoules of energy to melt 1 mole of H2O. That's the definition of delta H of fusion. It's always kilojoules per mole per 1 mole of something. And how you define what you're doing to that 1 mole defines what the delta H is. Delta H of fusion, it's 1 mole undergoing this phase change. Okay, so if I were to write the delta H of this reaction, in this case, this reaction here, where we're going from solid to liquid, that would be positive 6.01 kilojoules per mole, right? Plain and simple. But what if we were doing the reverse? What if we described this reaction, H2O liquid going to H2O solid? Okay. Would this be an endothermic or an exothermic reaction? It's exothermic because now we're taking energy out of the system. I think we all know if you have some liquid H2O and you want to turn it into solid, you remove energy from the system, right? And that slows things down and it gets it to convert into the solid phase. So this is now an exothermic reaction. Which means delta H is going to be less than 1, less than 0. It's a negative number. Okay, but what's the energy component? The energy component is still the same. It still takes 6.01 kilojoules of energy for 1 mole of water to make this transition, except now we're going in reverse. So the delta H for this reaction is going to be what? What do you think? Negative 6.01 kilojoules per mole. Very good. Negative 6.01 kilojoules per mole. Remember, the negative and the positive, it's not negative energy and it's not positive energy. The negative and positive sign is just telling you the direction of flow, either into the system, from the surroundings, or from the system into the surroundings. But the absolute value of the energy component is the same, whether you're going forward or reverse. It takes the same amount of energy. All right, very good. So the same discussion we would have if we're talking about the delta H of vaporization. Except now with vaporization, we're going from the liquid phase to the gas phase. If you look down here in the lower right-hand corner of this table, all right, here's the delta H of vaporization. It's also in kilojoules per mole. And when we look at it for water, you'll see that there's a number of different values depending on what temperature the water is at. And there's a reason for that, but to explain why that is kind of beyond the scope of what we need to be doing in this class, okay? But you can think of it as the closer you are to the boiling point, the less energy it takes to get to that boiling point and then convert from the liquid phase to the gas phase. Because you don't undergo that conversion until you're at 100 degrees Celsius. All right, so we have different values here if you wanted to also factor in what it takes to get to 100 degrees, and then once you're at 100 degrees, undergo that phase change. But for this class, we're just going to be working with this number here, the energy that it takes to convert 1 mole of H2O from the liquid phase to the solid phase, to the gas phase, sorry. So in this case, delta H of vaporization, right, this is equal to 40.7 kilojoules per mole. And I'm not putting a positive or a negative sign on that because that is completely dependent on which direction you're doing the experiment. If you're moving from liquid to gas, it's positive 40.7. If you're going from gas and you're cooling it down to the liquid, then we use a negative sign. Now, when we're using our equation, here, let's write that down. When we're going from H2O liquid to H2O gas, then delta H of the reaction is positive 40.7 kilojoules per mole. But if we're going from H2O gas H, the delta H for the reaction is negative 40.7. Okay, so now we're going to wrap all this together and do a big, massive mathematical calculation, right? It's going to look scary, but really all it is these equations, well, these two and this one up here, the Q equals mCp delta T, all right? But we have to do it several times to account for these 5 different components of our heating curve, because each component has a different enthalpy value that's dictated by different parameters, as we've been discussing. So this next slide has a lot of white space, which you know by now is dangerous for me because I like writing in white space. All right, but the math is very straightforward. It's just using those calculations and then a little bit of dimensional analysis. So I'm going to take you through that very slowly. And at each step, we're going to reinforce what we're thinking about with these different parameters. So first, let's just read the question. How much energy is required to raise 50 grams of ice, started at minus 18 degrees Celsius, and we're only going to take it up to 65 degrees. So we're going to stay in the liquid. We're not even going to take it into the gas. But this is enough to show you the different steps that you need to be paying attention to. My recommendation, anytime you approach a problem like this, that you know, okay, I have to split this into different parts. This is going to be a multi-step calculation. So we've been talking about these curves. Make yourself a little sketch. You know what these curves look like. We're going to start at minus 18 degrees. We're working with water, so we're going to take it through the melting point, which is 0 degrees Celsius. And we're not going to go up to the boiling point, which is 100 degrees. We're stopping at 65 degrees. So you'll know what these curves look like. So we're going to have how many components to this curve? Let's just show of hands with your numbers up. 1, 2, 3, 4, or 5 components are we going to have to work with? What do you think? Nice and high. I have a 3. I have a 3. 3. Anyone else? Everyone shot. 3 over there. 3. Or is that a 4? 3. Anyone else? Yeah. There's 3 components. Okay. Let's draw them out. We're starting at minus 18 degrees. We're going up to the melting point. And then when we're at the melting point, we're going to have a component here where the temperature doesn't change. And then once we get all into the liquid phase, it's going to now increase in temperature until we get to 65 degrees. And that's where we're going to stop. So let's divide this into 3 parts, part A, part B, and part C. So in part A, what are we doing in part A? In part A, we've got a solid. And we're taking that solid from minus 18 degrees Celsius up to 0 degrees Celsius. So let's just write down what's that energy component that it takes for 50 grams of ice at minus 18 to go to 0 degrees Celsius. So for that, we need this equation, Q equals the mass times the specific heat capacity of water at, of H2O in the solid phase, times whatever the change in temperature is going to be. And again, that's T final minus T initial. Well, let's write this down. So we know what the mass is. The mass is 50 grams of H2O. What's the specific heat capacity of H2O in the solid phase? Well, that we need to look up, or you would be given that in a table. It's not in this one. We have to go up to somewhere up here. Where is it? It's way up here. Here we go. H2O in the solid phase right here, 2.11. That's joules per gram degree Celsius. See up here? Joules per gram degree Celsius. Now keep in mind using the molar heat capacity. So they might be giving you this number, 38. Okay, but that's just joules per mole degree Celsius. And you know how to go between grams and moles of H2O. That's the only difference between this number and this number. Okay. All right, so we want 2.11. Slide whiplash once again. So this is going to be 2.11 joules of energy for every gram that's raised every 1 degree Celsius. Okay. And now what's the delta T going to be? It's T final minus T initial. So T final is 0.0 degrees Celsius minus T initial, which is minus 18 degrees Celsius. So minus and a minus, that's positive. So our delta T is positive 18 degrees Celsius. Agreed? Okay, so let's calculate that. Gives me 1899. Now, what are the units? Joule, very good. Now, I'm careful to put my units in. I'm always encouraging you, put your units in so that you can do this and make sure that you set everything up correctly. Units cancel out and it gives you the units of joules. Very good. So it takes 1899 joules of energy to take 50 grams of H2O and move it from minus 18 degrees to 0 degrees. So now we've done section A. Now we're at section B. We're going to continue to add energy, but now that energy is going into the phase transition. So let's notate that completely separately, and let's make a note to ourselves what we're doing in phase B so that you can stay focused on the right math that you need to do. So now we're at the melting point at MP, which is also the freezing point if we were going the other way. That's 0 degrees Celsius. And so now what we're doing in phase B is we're going from the solid phase to the liquid phase. There's no change in temperature. So we can't use our Q equals MC sub P delta T equation. We have to use a different parameter. That's going to be what? What are we going to use here? Delta H of what? Fusion or vaporization? Fusion. That's right. So we need the delta H of fusion here. So let's calculate our Q. In this case, it's going to be the delta H of fusion, which was our 6.01, if you remember. Okay. Now we're going from the solid to the liquid. So is that going to be, for the reaction, is that a positive 6.01 or a negative 6.01? It's positive because we're adding energy to the H2O to get it to go from solid to liquid. So this is a positive, and this is in kilojoules per mole. Now you got to be careful when you're in joules and when you're in kilojoules, okay? This is kilojoules per mole. And just so you know what we're working with here, this is the delta H of fusion. Now, we're given grams, not moles. So we do need to convert between grams and moles. It doesn't matter whether you're using the specific heat capacity in part A or the molar heat capacity in part A. At some point in these calculations, you have to convert from grams to moles. So let's just work through this. So we need to know, in this case, how many moles we have, because we haven't been told that. So we could calculate that separately, or we can just put that into our calculation here and use dimensional analysis. So we're given 50 grams of H2O. Now, who remembers the molar mass of H2O without having to calculate it? 18.015. That's right. Of course, if you don't remember it, you know how to calculate it. There's 18.015. Now, let's make sure that we put the right number with the right units in the right position. We want grams of H2O to cancel. Okay. So this is our mass of water. This is the molar mass of water. But in this case, we're using the inverse of it so that our units cancel out. Remember, molar mass, we're using it here as a conversion factor, converting from grams to moles. So now let's make sure our units cancel out. We have moles here, grams of H2O, grams of H2O. So now we're going to be left with the units of kilojoules. That's okay. But it's important to keep track of it. Here, I guess my answers are in red, so let's keep it in red. And that gives me 16.681. That's kilojoules. Okay, that's a lot. It takes 16.681 kilojoules of energy to take 50 grams of water, 50 grams of H2O and have it convert from the solid phase to the liquid phase. Okay? So that's now part B. Now we're all in the liquid phase, so now we're going to do part C, right? In part C, we're now all liquid, and we're going to now move it from 0 degrees Celsius up to 65 degrees Celsius. Okay, so we're going to do Q is equal to M C sub P delta T. Once again, in this case, the mass is still 50 grams. Now we can use the specific heat capacity of liquid H2O. We remember what that one is because we use it all the time. That's your 4.184 joules per gram degree Celsius. And what's our delta T going to be? T final is 65 degrees minus T initial, which is 0. So this is going to be positive 65 degrees Celsius. Let's calculate that. 13,598. What's my units? Joules of energy to take 50 grams of H2O in the liquid phase and move it 65 degrees Celsius. Okay? And that's all we're asked to do. So that's where we stop. But you can see how this would continue if we needed to go to different parts of the heating curve. And if we were starting at 65 degrees, and the question was asking how much energy is related to taking it from 65 degrees down to minus 18 degrees, we would do all of this. The numbers, the absolute value of these numbers would all be the same. The only thing that would be different is the sign. It would all be negative because now we're taking energy out of the system. But now we need to be careful because some of our numbers are in joules and some are in kilojoules. So we need to get these all the same. And since we're going to be calculating the, well, you could do it either way because we're not doing delta H per mole. I mean, we could calculate an overall delta H of reaction per mole. Actually, why don't we do that? Because we know how many moles that is. So let's get this all into kilojoules. So if I make this all into kilojoules, right, this is going to be, let's just round this now, 1.9 kilojoules. This is 16.7 kilojoules. And this would be 13.6 kilojoules. We add this up, we've got 15, 22, 12, 32.2 kilojoules of energy to take 50 grams of H2O and move it from minus 18 degrees Celsius to 65 degrees Celsius. All right, so that's our total. Now, if we wanted to express this as delta H of reaction, that would be the amount of energy in kilojoules, 32.2 kilojoules, divided by the moles, by 1 mole. Well, how many moles did we actually react? Well, it's buried in here. It's 50 divided by 18.015. So we need to do that. We have 50 grams, and it's 18.015 grams per mole. That will give us moles in the denominator. So we can actually calculate what the delta H of this reaction is. Should be 11.6 kilojoules per mole. If you wanted to tidy all this up into one number that describes all 3 parts together. So it just depends on what the question is asking for. Is the question going to ask for how much energy or what's the delta H? In this case, the question was asking how much energy is required, which means that this would be our final answer because that's what we're actually asked. How much energy? We're not asked for delta H of the reaction. We just calculated it for fun. Yeah.
I had a question about like any of them based on the pressure.
This part here? Yeah. Oh, that's a great question. Right? Wouldn't these values change based on the pressure? You're absolutely right, they would. But if you remember way back when we first started defining enthalpy, okay, we're at constant pressure. So enthalpy specifically Here, I'm glad you asked that. Let's just emphasize this. This just goes back to the original definition of enthalpy, which is way up here, okay, at constant pressure. Okay. But yes, pressure does affect these things. And if you want to learn more about that, then you should take physical chemistry. Try to keep it somewhat simple here, but that was an excellent question. Okay, so if you didn't get all of that in your notes, of course, this is recorded, so you can watch it again, all right? I tried to go really slowly and explain each step. So these look complicated, but they're really not. It's just merging a bunch of different steps together. And part of the process, again, I strongly recommend draw yourself a little figure so you know where you're going before you start. Don't just come across a problem like this and just blindly just start crunching away thinking that you know the path. Maybe it's going forwards, maybe it's going backwards. Know which components of this heating curve you're going to go through, and then make sure you use the correct values depending where you are. So now let's talk about something new, although I did introduce this for you on the very first lecture. The whole idea behind thermochemistry, okay, is that we're dealing with thermal energy as a component of the reaction. Okay, so let me just remind you of that. We're using heat now, or heat energy, as either a reactant or a product in our reaction. Just like C4H10, butane. For those of you who go on to organic chemistry, this is butane. This is a reaction, the combustion of butane. Should we balance it? Do you remember how to balance these? Don't start with oxygen, right? It's present in multiple places on one side or the other. And we also have it isolated by itself, which might mean that you want to save that for last to do our balancing. 4 times 2 is 8 oxygens plus 5 oxygens equals 13 oxygens. So how do we get 13 oxygens on the left-hand side? 13 halves, right? And now we need to get rid of the fraction. So we're going to multiply everything by the denominator. That puts the 2 here, changes this to a 13, changes this to an 8, and this to a 10. All right, now we have a balanced equation. Good, that was fun. All right, but now let's consider heat energy as a reactant or a product. What do you think? Is heat going to be a reactant in this reaction, or is heat a product in this reaction? What do you do when you light a fire? Does it give off heat? Yeah, so heat's a product, okay? Is this reaction endothermic or exothermic? It's an exothermic reaction because energy is given off by the system to the surroundings. That's why you get warmer, because you're in the surroundings. The combustion reaction is giving off energy. You're feeling that thermal energy as a rise in temperature. Okay, so if I write now the energy component of this, delta H of this reaction, is it going to have a positive sign or a negative sign? Very good, because it's an exothermic reaction. So delta H is a negative value, and now you need to look it up. It's 54 kilojoules per mole. When we write a chemical reaction like this, and also include the enthalpy components, that's what's called the thermochemical equation. All right, so by definition, that's what a thermochemical equation is. It has the enthalpy components. All right, this includes the delta H value associated with it. So here, let's highlight that. As part of your definitions. So let's consider then, this is a combustion reaction. Let's consider the delta H of combustion, right? This is the reaction that I just described for you here, where we have 2 moles of butane combining with 13 moles of O2 will combust and give us 8 moles of CO2 and 10 moles of H2O. But if I want to now define the delta H of combustion, this is specifically going to be the enthalpy, the change in enthalpy related specific to 1 mole of butane. Remember, when we specify a particular delta H of something, it's per mole now of that material. This reaction, the minus 5754 kilojoules per mole, that's how much energy is released when we combust 2 moles of butane. If you look up the delta H of combustion, it's going to be for 1 mole. Okay. So we need to write a reaction that defines the combustion of 1 mole of butane. A balanced reaction. That's going to look like this. C4H10 gas, that's 1 mole. So now we need to use the fraction. Okay. Because we know, I mean, we balanced it, so we know that it's going to be 13 halves. We'll produce 4 moles of CO2 gas. All right, this is one of those exceptions where we will have a fraction. We're forced to use a fraction because we are now forced into a definition for 1 mole. Must use fraction if you have to, because now we're specifying for 1 mole combusted. But what's that going to do to the reaction, right? If we were to write the delta H for this now, for 1 mole, what's it going to be? Is it going to be negative 5754 kilojoules per mole? It won't be, okay? Because now we're only combusting half as much. So we're only going to release half as much of the energy. So now that's going to be equal to negative 2877 kilojoules per mole. Now you might say, well, that's crazy because it's per mole, kilojoules per mole. So this is the mind-bending part of it, right? This is per mole of the reaction. Per mole of the reaction as written. This is mole of the reaction as written. Meaning 2 moles of butane being combusted, okay? In this case, the delta H, if we're combusting 1 mole, again, this is per mole of the reaction as written. But if you treat heat energy as a reactant or a product, just think of it as it's another compound in your reaction. If we have to cut all of the coefficients in half because we're describing for combustion of 1 mole, then we cut the heat in half. If for some reason we had to double everything, then you would double the amount of heat. And what do you suppose would happen if we ran this reaction in reverse? Let's write that in reverse. Here, let's take the top one and write it in reverse. That would be 8 moles of carbon dioxide gas plus 10 moles of H2O liquid. And let's say we can get that to react and give us 13 moles of oxygen gas and 2 moles of butane. It's unlikely that you can actually get this reaction to work, but we can think about it. Let's say we could run this reaction in reverse. And I wanted to describe this as a thermochemical reaction. What would the delta H of this reaction be? What do you think? Positive what? Positive 5754, that's right. 5754 kilojoules per mole. The value doesn't change. This is just like what we did with the delta H of fusion and the delta H of vaporization. The sign will change from positive to negative depending on which direction the reaction is going. But the value, the absolute value of the energy being exchanged is exactly the same. So all I'm doing here is manipulating the reaction along with the energy components of that reaction. And all reactions have an energy component. We just usually don't write it or take it into account unless you care about following the thermal energy. That's what we're doing with thermochemical equations. Okay, so the upshot of this is that whatever we do to the equation, you want to do the same thing to the energy or to the delta H. Do the same with delta H of the reaction. And we can do this because delta H is a state function as well. You remember what state functions are, right? It means that the value that we calculate is an equilibrium state, but we're moving from one equilibrium state to another when we're doing a reaction. And it doesn't matter how we get from one state to another, the change from state 1 to state 2 will always be the same. So that's the constant. I really like the mountain analogy. Okay, so let's draw our little mountaintop again, just to remind you. It doesn't matter, here's state 1 and here's state 2. And if we take this path, we'll have some change in that state function. In this case, it's altitude or potential energy, okay? Or we can take another path that gets to the same ending state. Doesn't matter how we get there. The difference between 1 and 2 will always be the same, okay? So it's independent of the path taken between the two equilibrium states. Okay, now we're going to be using the fact that delta H is a state function, and we're going to be using this property of thermochemical equations that we can cut them in half, or we can multiply them, or we can turn them in reverse, and we can manipulate the delta H value that is associated with them. And we can use that to calculate the delta H of reactions that can't be easily measured, but using reactions that can be measured easily. What do I mean by that? That's what Hess's law is all about. All right, so I'm going to introduce it now, and then we're going to working on Hess's law for the rest of these lectures next week, okay? Here's a fake reaction. ABC goes into AB plus C. And there's some delta H of reaction there. There should have been much more of a space here. Sorry that there's not a space. Let's just separate it by doing that, okay? Let's just focus on the reaction right now. And let's say we can do this, well, we want to do it in a coffee cup calorimeter, because you know from lab that in coffee cup calorimeters, you can actually measure what the Q is, right? Here, let's change colors here. So in a coffee cup calorimeter, you know all about, now you guys are experts on using Q equals M CP delta T to calculate what the thermal energy is of that reaction. And you know how to then get that into a delta H. Well, you can't do it for this reaction. But let's say you can do two reactions that you can measure in a coffee cup calorimeter. Let's say we can do a reaction where ABC instead gets turned into A plus B plus C. Let's call this reaction 1. Let's call this reaction 2. And then in a third reaction, we have A plus B goes to AB. Reaction 3. And let's say that we can't measure reaction 1 in a coffee cup calorimeter. It's just not convenient. Maybe it's a combustion reaction or whatever. But we can measure reaction 2 and we can measure reaction 3 in a coffee cup calorimeter. So here we can measure Q for reaction 2 and reaction 3. Okay, but not for 1. So notice that these two reactions actually add up. All right, if I take ABC goes to A plus B plus C, that's reaction 2. All right, here let's just put a little 2 here. And if I take reaction 3, that's going to be A plus B C goes to, oops, sorry, I did made a mistake. A plus B goes to AB here. My mistake. When we add these up, we get ABC goes to AB plus C. So if we can add them up here on the right, and if we can measure the enthalpies related to reaction 2 and reaction 3 in our coffee cup calorimeter, we can actually come up with what the delta H of the reaction is. That's simply going to be the delta H of reaction 2 plus the delta H of reaction 3, because that's what we did here. We added 2 plus 3. So treating the enthalpy as part of the reaction. All right, whatever you do to the reaction, you do to the enthalpy. And if we can add those reactions together to explain the third one, then we can just add the enthalpies together and calculate the third one. Okay, so that's a preview for Hess's law. We'll be exploring that in more detail next week.